In the last video, we were happily implementing our server until we reached the compilation error. Let's see what this error was. If we try to build our code, we see that the compiler complains that the server new associated function expects a string, but it actually found a lowercase str. Looks like the string literal that we are passing to the function is not of a type string. So Rust has two types of strings, and let's dive deeper into them to figure out what they are. This thing here, the lowercase str, is called a string slice. A string slice is an immutable reference to a part of a string. If you're coming from the C++ world, a string slice is similar to the string view. Okay, let's see that in action. We can comment out the existing code that we already have. And up here, let's create a new variable. We'll call it string. And as we remember, to create a new string, we can call the new associated function of a string. But in this case, we actually want our string to have some value. So we can call from on a string. And in here, we can pass the IP address that we have. Now, this will create a new string. It will allocate it on the heap for us, and it will fill it with this information. Great. As we said, a string slice is a view inside of an existing string. Let's imagine that we want to extract the port from this address here. One way to do it would be to explode the string on the dots here and then copy the second part into a new string, but that would require heap allocation, and we really don't want that. In Rust, we can actually use a string slice, which is just a borrow of an existing string. So if we borrow our existing string, and it has this special syntax at the end where we can specify the range of symbols that we would like for our string slice. In this case, if we only want the last 4, we know that this has a length of 14, so we want the characters from the 10th to the 14th one. This is the syntax that's used to specify ranges in Rust. A neat trick that we can do here is, because we want all symbols after the 10th index, so we do not need to specify an upper bound. If we just omit that, that is still valid, and Rust will give us all characters starting from this up until the end of the string. The same thing would work for the beginning of the string. For example, if we want the first 3, we can say 0 to 3, or we can just say ... 3, and that will work in the same way. Okay, so let's leave it like this for now. Let's log our two strings. Here we can log our string, and we can also log our string slice. Looks like we have an error here. Before I actually show you what the error message is and explain the error, I want you to pause the video and try and figure it out yourself. As a hint, I will just mention again that the string slice is borrowing the string that we already have. So pause the video now and try to figure out why the compiler might complain here. Okay, I hope you paused the video. I hope you got it right. Let's see what the error is. Yeah, as expected, it's complaining that it cannot move the string variable because it is already borrowed. So we have borrowed the string variable here, but we're giving ownership to the debug macro, which will call some functions underneath. The way we fix this is by actually passing a reference to our string instead of giving ownership to it. So now, whatever the debug macro actually expands into, we'll just borrow the string. It will not take ownership of it. Okay, great. Now let's run our code and see what it will output. We see that our string has its full value, and we see that our string slice is only the last 4 characters of the string. Let's explore the memory layout of these two types of strings. Here we see that we have our stack and we have our heap. Let's imagine that we have allocated some string on the heap. The size of one of these boxes is 1 byte, just for reference. The number at the bottom is the index in the string, and the value at the top is the actual character that we have stored. All right, we have our string. How would we represent this on the stack? This is how it would look like on the stack. We store the length of the string. So at this point, our length is 10 bytes, as we can see. So we store the length. We store the capacity. The capacity is all the bytes that we have actually allocated for this string. In this case, we can see that we have allocated 12 bytes because we have 2 bytes at the end that we're not using at the moment, but they're still available to our string. Strings in Rust can dynamically grow or shrink. For example, now if we were to push a character to the end of the string, it would use the existing free capacity that we already have. If we push too many characters and they cannot fit in the free capacity, a new buffer that is bigger will be allocated somewhere else on the heap, and the entire string will be moved there, and then the string can keep growing. Okay, and the last thing we store on the stack is just a pointer to the beginning of the string. This is all the information that we need to be able to use the string. We know that where the string starts and we know how long it is. So our code can actually come here and read the entire string. So far, so good. Let's imagine that we're writing a program that we want to explode the string on the space here and only take the second part of it. One way we can do this is, we start looping through all the characters in the string. When we find the space, we just copy the rest of the bytes that we have here, in this case 3 bytes. We copy them into a new string, so we allocate a new string on the heap, we copy this data there, and we return a pointer to this new string. That would work, but it means a new heap allocation, and we will also need to store this data twice. In a lot of cases, we would not want to store the data twice and allocate again because we only want to read the data. If we don't need to modify the data, it makes no sense to have it in another place. We don't need to take ownership of it. We can only point to the data inside of this string. So this is where string slices come in. If we have a string slice here, it will just have the length of the slice that it wants and a pointer into the existing string. So now we know that our string slice starts from here and it has a length 3, so we can only actually work with these 3 characters. Our string slice does not see the rest of the string and cannot use it. This is a very efficient way to work with strings. Later in this course, we will have to write our own HTTP parser. So there we will use string slices because our HTTP request will be allocated in a big buffer, and we would want to have different string slices to the method or the query parameters or the path. It makes no sense to copy them every time because we would not want to mutate them. We only want to read them. So string slices will let us efficiently dissect the requests that we would receive in our server. Let's talk about some other cool features of strings and string slices. For example, the compiler can transparently convert a string into a string slice for us. If we want to pass a string to a function that actually accepts a string slice, the compiler will convert this string into a string slice and pass that to the function. It will just be a string slice that points to the entire string. Let's see that in action. If we say that we want to borrow our entire string, but we actually want it to be of type string slice, we can borrow the string, or if I could type, we can borrow the string in this way, and that will compile. The compiler is perfectly happy with it. As we can see, it will just convert this into a string slice that points to the entire string. Okay, and the last thing, which was actually the root of our problem here, is the string literals. If we have a string literal, so we have a variable called string literal, and it is equal to the string 1, 2, 3, 4. How does that work? So because this string literal is known at compile time, we tell it to the compiler before we actually compile our code, it will bake it into the binary itself. So there will be some region in memory where this string actually lives. And in here, this will be a string slice to the entirety of this string. Let's think about why we actually want to use string slices and not normal strings for this. As we said, normal strings can be expanded or they can shrink dynamically at runtime, but string slices are immutable. This string is immutable because we specify it in its entirety at compile time, so we will never want to change it at runtime. So a string slice would be an immutable view of this entire string. Let's actually print the rest of our strings here. So we want to print our string borrow and our string literal. Okay, if we run our code, yeah, we see that everything prints out just fine. Our borrow just prints the entire string. Our literal prints its value. There's one last thing to discuss regarding strings and string slices. Generally, we would not want to slice strings with literal indexes like this. The reason is that all strings in Rust are UTF-8 encoded. What that means is that we cannot be sure that one character in the string will always take up 1 byte. As we know, all ASCII characters, which is the English alphabet, the numbers, and the most common symbols, are also encoded in UTF-8 using the ASCII encoding, so they all take up 1 byte. But for example, if we want to use a Cyrillic alphabet or some Japanese symbols or some emojis, they will take up more than 1 byte. The reason this can be a problem is when we slice a string like this does not mean give me everything after the 10th character. This actually means give me everything after the 10th byte. So in this case, here we know that every single character is encoded into a single byte. So for this string, the 10th byte and the 10th character are exactly the same. But if we had a string that looks like this, we have these nice emojis, which is something that everyone wants, a burger, some fries, and 2 beers. Nothing beats that really. And if we just want to index that, we want to take the first 4 characters, let's say. All right. If we run our code, we will see that our string slice only outputs the hamburger. It does not output all of them. The reason is that this hamburger emoji is actually encoded in 4 bytes instead of 1 for English characters, for example. As we said, Rust strings can only store valid UTF-8. So this can be very dangerous because if, for example, we want to take the first 5 bytes, now we take these whole characters plus some part of the next character, but not the whole next character. And if we actually try to run this, our program will crash and Rust will again give us an amazing error message. It will tell us that index 5 is not a character boundary, as we already know, and it will also tell us that index 5 is inside of this character and that this character actually occupies these 4 bytes between index 4 and 8, this string. So now we know that this character ends at index 8. So if we change this to 8, our code will work again. Great, now we get the first 2 characters. But this is still dangerous because let's say, for example, we swap this first character with a Cyrillic one. Let's say this one. Now, if we actually want to run our code again, it will fail again because now the boundaries are not where we expect them because the Cyrillic character only takes up 2 bytes instead of 4. So generally, when we are writing real-world applications, we would not want to directly slice into strings like that because this can easily fail at runtime. There are functions that, like find, for example, that can find the space in a string and they will give us back an index, and we know that this index is valid. This is the way we will actually slice into strings. All right, let's delete all of this code. Let's uncomment what we already had. Let's try to build our code again, just so we can see what the error message was. So again, Rust tells us it expects a string, we pass it a string slice, but it also tells us exactly how to fix it. It tells us that we can call toString on the string literal. Let's try that. If we just call toString here, this should convert our string literal into a string. As we can see, that works. So this pretty much will take all of this and convert it into an actual string and allocate it somewhere on the heap. A last thing that we can do here is actually add a log line to our run function. So we can actually say that our server is listening on some address. And here we can use our self reference to actually put the address that we want. Now, if we run our code again, we see that we are listening on localhost port 8080.